This is Concept 1 Notes and our 9th unit on acids and bases, and we are going to be talking about how to define acids and bases. So, a little overview. I have mentioned before neutralization reactions. This is another word for an acid-base reaction, and it is a specific type of a double replacement reaction of an acid and a base, and they react to form water and salt. And if you are an honor student listening to this, we talked about this back in Unit 4, chemical bonds. We learned some naming rules. We mentioned acids, and we mentioned this type of reaction in Unit 5, chemical reactions. This is going to be a little bit more new to you if you are in the non-honors group. But this is just, again, a specific type of double displacement or double replacement reaction. And what we see is that substances with opposite properties tend to react with one another. So I kind of color-coded these. Here's an example of a neutralization reaction. You have the acid, which is the hydrochloric acid here. You have the base, which is sodium hydroxide. They react to make a salt, which is sodium chloride, and then also water. So literally this whole concept is about defining acids and bases. So I'm going to give you a definition right now just for the sake of clarity, but we're going to keep adding on to this as the unit goes on. So an acid, that's why I put an asterisk here. An acid is a substance that makes hydrogen ions when it's dissolved in water. So like this hydrochloric acid, when it's in water, the water pulls the hydrogen to it, making H3O plus, which is a hydronium ion, and then it leaves the chlorine by itself, which is a Cl minus. The base is a substance that makes hydroxide ions when dissolved in water. So looking at that sodium hydroxide, if this was going to go into water, it would dissociate into sodium ions and hydroxide ions. That's what we would see there. A salt is an ionic compound made from the cation of a base and the anion from an acid. So look at the sodium chloride. The cation, sodium, came from the base. The anion, the chlorine, came from the acid. And then, of course, we know what water is. But again, remember, these are very oversimplified definitions, and we're going to dive further into how to define them as we move forward. And then we're also going to talk more about neutralization reactions later in Concept 3. So just kind of hold tight here. So let's go over some of these definitions for the ways that we can define acids and bases. So one type of theory where these definitions come from is the Arrhenius theory. And this came from a Swedish chemist. I'm going to totally butcher his first name. Svante Arrhenius, I think is how you pronounce it. And he, theorized that an Arrhenius acid is a chemical compound that increases the concentration of hydrogen ions in an aqueous solution. So how this happens is that the acid will ionize in a way that increases the amount of hydrogen ions that are present. So what does ionize mean, or what is ionization? That's when ions form from a covalent compound like an acid. So this is a slight distinction from dissociation. Think about HCl, hydrochloric acid, which we just talked about on the last slide. HCl, that is a covalent compound between the hydrogen and the chlorine, but it's very, very polar. Okay, so it's going to dissociate and separate, but it's going to separate into ions of a hydrogen ion and a chlorine ion. So we say, instead of saying that it dissociates, we say it would ionize in that way. Like I just said, acid molecules are really polar. Some are more polar than others. Thus, water molecules attract their hydrogen atoms because remember, water is polar. And that's how we get this hydronium ion, this H3O plus. Water will pull in those free hydrogen ions that the acid adds to solution. And that's how we get this hydronium ion. So for example, right here, HClO3 is an acid. When we put it in water, what we see happen is it ionizes, it separates, and it forms two ions. It forms hydrogen ions and these chloride ions, and then the hydrogen ions are attracted to the water, and that's where we get this H3O plus. So we're increasing the concentration of hydrogen ions in a solution. If you want kind of like a general equation for this, we typically see the acid with the hydrogen on the front, and then it's with water, and then it's going to make, the anion from the acid here, and then we're going to see H3O plus as well. Now, Arrhenius also had a definition for a base, and a base is a substance that increases the concentration of hydroxide ions in an aqueous solution. So that's going to, add OH minus to the solution. Now, Some Arrhenius bases are really obvious. They're ionic substances that have hydroxides in them. Sodium hydroxide, potassium hydroxide, calcium hydroxide. These will dissociate into their ions, and boom, all of a sudden you have hydroxide ions in the water. Again, we're saying dissociate because typically bases like this are already ionic. They already have ionic bonds. So we only use the word ionize with acids if it starts as a covalent bond. But since these are already, ionic compounds with ions in them, they're just dissociating into their ion form. So an example of this, sodium hydroxide, we have water over here. Now notice that I didn't, really put it as a reactant. I put it over the arrow. Because remember I said bases tend to be ionic compounds that are just naturally going to dissociate into their ions here. And they're just going to separate that way. So that's why this is kind of written up here. But we see that it dissociates into the sodium ion and the hydroxide ion. Thus, we're adding hydroxide ions to the solution, thus meeting this definition of an Arrhenius base. And kind of a general equation for this is the base has some sort of hydroxide in it, and then it dissociates into whatever, its cation is, and then the hydroxide ion. Now, this isn't always the case. Some Arrhenius bases are substances that react with water and they remove a hydrogen ion from the water, and then that leaves hydroxide left in the solution from the water. So we see this with ammonia here. We see this here as well with the CH3NH2. So let's look at this ammonia and how this does this. So what this ammonia does, it's polar. It's going to pull the hydrogen off of the water, adds it here. So now we have NH4 plus, and then it's left that hydroxide ion here. Still fits this definition because it's increasing the concentration of hydroxide ions in the solution, but it's just doing it with a different methodology. Okay, now, not all acids and bases that we would consider acids and bases even fall under those definitions. So we have an even more broad definition we can use to define acids and bases. And that follows along with a different chemist, a Danish chemist this time, and an English chemist. And their names were Bronsted-Lowry. And their theory kind of expanded on Arrhenius's and broadened the definition for acid and base. So first, Bronsted-Lowry, they looked at acid-base reactions, and they saw that protons get transferred from one reactant, the acid, to the other, which is the base. And so that's kind of how they came up with their definitions that are, again, a little bit more broad. So a Bronsted-Lowry acid is a proton donor, and it donates a proton in the form of the hydrogen ion that it's going to be, giving typically, to water. A Bronsted-Lowry base is a proton acceptor, which is typically in the form of a hydrogen ion that it is going to receive. Okay, so for example, look at this reaction of hydrochloric acid, and we put it in water. We see that hydrochloric acid in this scenario is an acid because it's going to donate that hydrogen to the water. Water in this scenario is a Bronsted-Lowry base. It would be classified as a base because it's going to accept that hydrogen from the hydrochloric acid, and that's what's going to make this here. Okay, so it's a proton acceptor. Now, another situation, look here. In this situation, what's a proton donor? The water's donating a proton, and it's going to donate it to the ammonia, which is going to be accepting it. So in this situation, water acts as an acid, and the ammonia is the base. And so this is where we get introduced to a new term, which is amphoteric. Water is amphoteric, which means it can act as an acid or it can act as a base, depending on what else is in the solution. So amphoteric applies to any substance that can act as an acid or base. Sometimes it donates a proton, sometimes it accepts a proton, dependent upon what else is in the solution. Now, there is another definition that even expands even further about this, and that's the Lewis acid and the Lewis base definitions. I'm not going to get into those with you guys because I think it only further complicates things, and I want you to really understand these two sets of definitions that we just covered. But if you are listening to this and you have a different teacher than me, then you might be expected to also know those Lewis acid and Lewis base definitions. So I just want to throw that out there. But for me, those two are good enough for my classes. Now, I want to, before I let you go, when we're talking about defining acids, we also see that there are kind of some characteristics that can be used, some properties that are all acids really share. So For instance, we see acids tend to have sour taste, and they can be corrosive to body tissues, especially if they're a high enough concentration. We see that acids react with some metals and they form hydrogen gas. That's something we can see. And then we also see that acids can react with carbonates and form carbon dioxide, which is something we can see when you have hydrochloric acid in your stomach, and we put if you take a Tums are mainly calcium carbonate. If you put a Tum in hydrochloric acid, it kind of bubbles, and that is the carbon dioxide that's being given off. And the same thing happens if you take like an Alka-Seltzer tablet. And one of the side effects of these Tums and Alka-Seltzer tablets is they can make you burp, and that's typically because of that carbon dioxide, which is kind of a fun fact there. Okay, so here's an example of this. We can see barium when it's reacting with an acid like we see here. It can make barium sulfate and hydrogen gas. And then another example here of an acid reacting with a carbonate like calcium carbonate, and it makes carbon dioxide and water, and then our salt here. Now, acids also react with bases to make salts and water in neutralization reactions. That's something we kind of talked about at the top of the episode of the video. And then we also see that acids form electrolytes in a solution, and thus they can typically conduct an electric current. They also cause a color change in indicators. For example, there's a ton of different types of indicators. Hopefully we can explore some of those in class together. But one example is if you ever have pH paper, when it's in a neutral solution like water, it's kind of like a yellowish green. But the more acidic solutions will give like red shades. So oranges and reds are the acidic shades that we see with the pH paper. Okay, now let's kind of compare and contrast this now with some properties of bases. So bases don't have a sour taste, they have a bitter taste. They can also be caustic, and they can burn and be harmful to body tissue. Diluted base solutions often feel slippery. Soap is a really diluted base, and so it feels slippery. Bases react with acids, and they make salts and water in neutralization reactions. They also form electrolytes in solution, and thus can conduct an electric current. They also cause a color change in indicators. And here's where we do see a difference. So pH paper will turn to more of the bluish shades, the blues and the purples, when it's in a basic solution. So acids turn the pH paper more orange and red. Bases turn it more blue and purple. Neutral solutions are like yellowish green. That's kind of where they're at. Okay, so that was kind of a lot. So now we're going to do a little summary chart together just to kind of organize all that information visually so you can keep it all straight.